Hey everyone, this is a perfect example of how to solve for a shear moment diagram given a simply loaded beam. So the first step in solving this type of question is solving for the reactions. So I'm going to go through this fairly quickly just because we've been doing this on every other problem in this class. So sum of the forces in the x equals 0. The only forces that are occurring in the x are happening here at this wall, and that would be RAX, right? So nothing else is competing with it. So we know that RAX equals 0 because sum of the forces in the x equals 0. Okay, so our next reaction would be sum of the forces in the y equals 0. So all the forces that are occurring in the y. So let's start over here. Sum of the forces in the y for RAY are positive because it's going up, and then our next force is this 8 kips going down, so that's minus 8. So pay attention here, this is where it gets a little tricky. This is considered a distributed load, meaning the forces are occurring evenly across the amount of feet that it's happening on. So the amount of feet would be the 8, and it's 2 kips per foot within this 8 feet. So you would do the 2 times the 8, because that's your force times the amount, or the distance. And then you would do just like a regular force, this 4 kips, minus 4 kips because it's going downwards, negative, equals 0. So add that all out. RAY, which was your unknown variable in which you were solving for, equals 28 kips. Okay, that's important. Keep that written down somewhere. Sum of the moment is next. Sum of the moment at RA, which is this one right here, this fixed connection, or this for this cantilever beam. Okay, so our first force that's occurring is this 8 kips, and we're going to do the 8 kips times the distance from the moment that we're solving at. So it's 8 times 4. And it's negative because if I were to put a pin here and I were to pull this force, it would be moving clockwise, which is a negative direction. Okay? Minus, this is where it also gets tricky because we're dealing with this distributed load, minus 2 times 8, because we know that the 2 kips is occurring at every foot over this 8 feet. So 2 times 8 times half of the distance that it's occurring. So half of this distance is 4. So 2 times 8, because that's the total, times 4, because that's half of the distance that the distributed load is occurring on. And if you notice I put this arrow right here, because in distributed loads, because they're distributed, we can denote that this force is occurring evenly in the middle, which is why we take this half distance, 4, plus the remaining distance from where we're calculating the moment, which happens to be 4, okay? Then moving on to our next force, the 4 kips, negative, because it's going in a clockwise direction, times its distance away from where we're solving in moment, which is 8 plus 4, so 12. Solve that out. Sum of the moment at RA equals negative 208 kips. Okay. So write these down. I'm going to put this sheet away so that it's easier for you to see what we do next. Actually, I wrote them out right here, so it's easier for you to see. Okay, so now when we're doing our shear, or V, diagram, it's easy to do this, but you have to refer back to the picture that's given, or the cantilever beam that's given, and its forces. So we know that the first force that occurs is the RAY, which is right here, and that's 28, positive 28. So that's what our first shift on this diagram will be, 28, okay? And I suggest you write these numbers out. It'll help you in the long run when it comes to the moment diagram. So now, look at the beam. Nothing is occurring, no forces are occurring between this 4-foot span. So that's just denoted as a straight line, okay? And we're still at that 28 feet, or not feet, 28, okay? So the next force that's occurring is a downward force of 8 kips. So it's as easy as subtracting. Downward force, 8 kips, we're now at, you guessed it, 20. Okay, so now this is where it gets a little tricky because of the distributed load. Because it's a distributed load, it means it's constantly occurring over that 8 feet at 2 kips per foot. So what you have to do is multiply the 2 times the 8, which is 16, and that's the number of force that's occurring, okay, over this span. Now, how we draw it is at a decline angle, okay? So, and that's occurring over the 8 feet. All right, so 2 times 8 was 16, so it was minus 16, which leaves us at 4, okay? Then our next force is the 4, which is exactly what you want to happen. You want your diagrams to hit the 0 line because that's how we know that we correctly calculated the forces on the beam, or in this case, the cantilever. All right, so the next part is dividing up the areas, and this is so that we can actually calculate the areas and then use that in our moment diagram. I'm actually going to end this video and upload another one, so click on the next video.